Legislation requires slope designs to meet appropriate standards to protect the safety of personnel working in and around coal mine slopes. On an open-cut coal mine site, geotechnical engineers are responsible for ensuring that the mine designs meet the industry geotechnical standards. This video explains the functions of geotechnical engineers in the mine planning and design process of an open-cut coal mine.
Geotechnical engineers examine rock and soil properties to determine their mechanical behaviour. On a mine site, geotechnical engineers must assess the geology, rock structure, strength, deformation and groundwater conditions for every area to be mined to determine a safe and economic design that complies with both statutory and company requirements. The mine geotechnical design and review process requires inputs from exploration, geology, mine planning, environmental, survey and operations. It's critical for geotechnical engineers to receive the information they require in a timely manner so that there's adequate time to review, change or optimise mine designs to comply with safety, economic and equipment constraints.
Types of data required by geotechnical engineers to enable effective design are discussed in terms of geological, structural, hydrogeological, geomechanical and spatial categories, the first four of which are required to create a robust geotechnical model. Geological data required includes base of soft weathering, base of hard weathering, rock type and persistent weak or hard units. The base of soft and hard weathering is required where the degree of weathering strongly influences rock mass properties. It is important to recognise that not all weathered rock is weak. Geotechnical engineers need the base of soft weathering to be differentiated from the base of hard weathering to ensure that appropriately shallow batter angles are planned for extremely weathered soil-like horizons, or conversely, to determine whether steeper batters can be excavated in moderately weathered but still competent rock mass horizons. Rock type is required to delineate the location and spatial variability of rock mass domains in geotechnical models. Geotechnical engineers want to classify rock types that will behave similarly. This is important for both excavated and dumped slope stability. Persistent significant units should be modelled as standalone surfaces in the geological model. Geotechnical engineers need to know if there are local or persistent weak bands that will destabilise the base of dumps, or that must be disrupted by blasting or ripping before placing dumped material on top. This type of geological data is acquired from exploration drilling and sampling, as well as the geophysical logging of exploration holes, using caliper, gamma, density, neutron logging tools. Structural data required includes faults, including their orientation, persistence and disturbance zone, joints, including their orientation, persistence, frequency and a number of joint sets, bedding plane orientation including the direction and magnitude of local rolls in stratigraphy, and bedding plane shears including their location, dip and dip direction. The geometry of persistent structures relative to planned excavation or dump orientations can have a significant effect on slope stability. By knowing the frequency, orientation and location of structure in advance, modifications to strip geometry can be made to engineer out potential stability issues that are structurally controlled. Provisions to actively manage failing material, such as incorporating appropriate bench widths, can also be built into the design. Recommendations and requirements for blasting can be made if this type of structural information is available. For example, geotechnical engineers can consider the direction of dominant jointing and provide recommendations on the firing direction of pre-splits and mid-splits in order to reduce backbreak and crest cracking. This type of structural data is acquired from exploration logging of core, geophysical logging using acoustic televiewer tools, 2D and 3D seismic programs to identify large-scale structure, and high wall mapping using laser scanner, drone or photogrammetry acquired data to quantify joint sets, spacing, orientation and persistence. All data acquired from exploration and structural mapping should be kept in a defect database. Hydrogeological data required includes standing water level or total head, piezometric pressure readings, and hydraulic conductivity and flow rates. The degree of saturation, seepage, groundwater flow, or build-up of pressure or depressurization behind a slope face can have a significant effect on excavated and dumped slope stability. By understanding groundwater conditions and flow behaviour, contingencies such as dewatering, depressurization, or slope geometry modifications can be made to ensure a safe slope design. Adequate pumping provisions can also minimise the impact of water on operations. Hydrogeological data can be acquired from standpipes and piezometers drilled at strategic locations around current and future excavations. Standing water levels may also be estimated from sonic logs if holes were not artificially filled with water during the exploration and geophysical logging process. Hydraulic conductivities can be measured using airlift, pumping or packet tests ahead of excavations. Hydraulic measurements should be acquired for the different rock mass domains encountered and not simplified or averaged. Geomechanical data required includes empirical measurements such as joint roughness or RQD estimations recorded during exploration logging, uniaxial compression strength, or commonly referred to UCS tests, or point load tests, density, Poisson's ratio, Young's modulus values, direct shear tests, triaxial tests, slate durability tests. Empirical rock mass and defect strengths are used for the determination of material strength in lieu of laboratory samples. UCS and triaxial tests are used to estimate rock mass strength for use in slope stability models. UCS test data is further used for the determination of appropriate powder factors for drill and blast planning, and for the determination of site-specific sonic UCS relationships to reduce the need for laboratory sampling as operations become more mature. Point load tests are required for the determination of rock mass strength, conversion to UCS strength in the absence of UCS tests, or to supplement UCS test results. Direct shear tests are required for the determination of defect strengths, for example, shear planes, joints, and bedding planes. Slate durability tests are required for the determination of susceptibility to degradation when exposed to water. These tests are particularly important for understanding how waste material will behave in dumps when exposed to water over long periods of time.
Geomechanical data can be acquired from laboratory testing of samples obtained from exploration drilling. Strength data is also estimated through the back analysis of failed slope geometries using geotechnical modelling software and either limit equilibrium, finite element, or synthetic rock mass modelling techniques.
Spatial data is typically sourced from mine planning engineers and the survey department, and includes mine planning designs such as truck dumps, dragline spoil, co-disposal dumps, high walls, end walls, soft walls, and blasting patterns, as built at mined out surfaces, and current topography showing locations of key infrastructure such as buildings, rail lines, water storage facilities and tailings dams relative to planned excavations or dumps. Mine plans should include information on the type of equipment being utilised to execute the design, such as which horizons will be excavated by truck and shovel, and which will be excavated by dragline. Dump designs should indicate where waste material will be sourced from, so that the design process can accommodate extremely weak or weathered material. With this information, mining engineers, drill and blast engineers, and geotechnical engineers work together to produce the optimum design geometry for mine safety and productivity. For example, geotechnical engineers want to avoid sharp 90-degree elbows or bull noses as much as possible in the mine design to minimise blast damage and exposure to adverse structure. If such geometries are observed in the mine plan, the geotech may make recommendations to modify slope geometry to improve stability.
Best practice is for geotechnical engineers to produce geotechnical design standards that mining engineers can reference to determine whether proposed slope designs meet predefined design acceptance criteria. Some sites include this information in their ground control management plan. Geotechnical design standards should include details of specific slope geometries like maximum batter angles, maximum bench heights and minimum bench widths for anticipated geotechnical conditions. If mine designs don't conform to the geotechnical design standards, the mining engineer should modify the design accordingly or discuss options with the geotech to achieve a safe slope design. As-built and mined-out surfaces are used to build slope stability models. Geotechnical engineers need this information to ensure conditions such as water or mud left in the previous mined-out strips are factored into the new design. The location of infrastructure is included in the design process to ensure that should slope failure occur, critical infrastructure is not adversely impacted.
Using the geological, hydrogeological, structural, geomechanical and spatial data described in the previous sections, the geotechnical engineer will define geotechnical domains. Geotechnical domains are areas or zones that have similar geotechnical characteristics and are not necessarily defined by lithological boundaries. Determine range of rock mass and defect strengths. Build and run stability models to determine the potential for slope failure. The type and level of detail required will be driven by the potential failure modes, failure mechanisms, and consequences of failure. The four main types of geotechnical assessment methods are empirical, using design charts or basing designs on the performance of previously excavated or dumped slopes in similar conditions. Kinematic, limit equilibrium, and numerical modelling. Modelling results may be reported in quantitative or qualitative terms. Qualitative, such as likely or unlikely, or quantitative, such as factor of safety, strength reduction factor, or probability of failure.
Factor of safety typically relates to results generated using limit equilibrium modelling techniques and is the ratio of the sum of the resisting forces around the failure surface divided by the sum of the driving forces. The strength reduction factor is often interchanged with factor of safety, but by correct definition is the factor by which the assumed shear strengths must be reduced by in order to achieve failure in the model. That is when the ratio of resisting to driving forces equals 1 and is generally calculated from models run using finite element analysis.
Probability of failure generally describes the number of model iterations that have achieved a factor of safety less than 1 divided by the total number of iterations computed. Each iteration contains a different combination of material strengths to capture the inherent variability in an excavated or dumped slope. Sensitivity analysis may instead be completed where the slope geometry and model inputs such as material strength or ground water level will be varied to determine the change in factor of safety. This determines how sensitive the model is to certain parameters and can reveal what the critical geometry is that may lead to unwanted slope failure.
Depending on modelling and sensitivity analysis results, modifications to designs are made to either ensure design acceptance criteria is met or to realise opportunities and increase mining efficiencies. Design modifications often include, but are not limited to, change in slope batter angle, change in strip orientation, change in slope height, change in location and dimensions of benches, introduction or change in buttress dimension or soft wall, stipulation of floor treatment before subsequent strip spoiling, stipulation of dewatering and or depressurization requirements, and stipulation of mining method to account for potential instability, such as retreat mining, backfilling by block, dragline digging offline, or defining a minimum equipment to crest offset.
The extent and magnitude of modifications made or recommended is generally dictated by a number of factors. They include how close the calculated factor of safety, strength reduction factor or probability of failure, is to the design acceptance criteria. If these are too high, there may be potential for optimization, or if too low, changes will be required to meet design requirements. Design acceptance criteria will vary depending on risk level, which should include consideration of the consequence of failure. This may be measured in terms of risk to human lives, cost or impact on production, environmental impact, or reputation.
The geotechnical design process is fundamental to a successful mining operation. Its primary aim is to engineer out or control slope failure. Without continuous updates of technical data by exploration, geology, environment, survey and mine planning, the geotechnical design can result in over or under designed slopes, which in the worst instance can result in unplanned slope movement. Open cut coal mining is a dynamic environment. Your contribution to the mine design process is critical for safe, efficient geotechnical designs to be delivered in a timely manner.